Welcome back to another exciting chemistry lesson. In the previous lesson, we learned how to write electron configuration using a periodic table. Now we are going to learn about the three important rules when we are going to interpret those electron configuration into orbital notation. Now we already learned about the Aufbau principle, basically saying that energy where electron will occupy the lowest energy level first, right? Which we can look at the period on the periodic table. Now let's talk about the other two rules that we need to know when we convert from electron configuration to orbital notation. The first one is called the Polyexclusion Principle. And based on this principle, think of the word exclusion. You exclude it, right? So to exclude, what does that really mean? Well, in this case, remember we talk about orbitals, how one single orbital can have two electrons, but electrons are negative, so one must go the other way, and the other one go up, the other one must go down. It's considered having opposite spin. So the reason behind this is Polyexclusion Principle saying that electron in the same orbital cannot have the same spin. So this is great, but this would be wrong, okay? Remember, electrons are negative, so they repel each other. It forces them to naturally go into the opposite spin. Well, the next rule we have is especially for the orbital diagram, and that is the Huns Rule. And the Huns Rule states that electrons always occupy an empty orbitals in a sublevel first before pairing it up. So let me show you how that works. Before we learn that different sublevel has different number of orbitals, right? For P, in this case, it has 3. So if I only have, 3 electrons, okay? If that's the case, one must go up, the other one go to the other one, and go to the other one. It makes sense because electrons are negative. They don't want to pair up unless they have to. And that's the logic behind Huns Rule. It would occupy the empty orbitals in the sublevel first. So if this would be incorrect right here, 1, 2, 3. If one go up, one go down, and then you have this 2 empty space that's not being used. So this would be violation of the Huns Rule. So let's look at some more example, okay? Here we have this right here go up, up. So what's happening here? You can see that this violate what? Well, it violates the Aufbau principle right there. So why is that? Well, think about it. This electron is supposed to go over here because it's occupied the lowest energy level first, because we still have that one space right there. How about this one? Go up, down, good, up, down, good, up, down, good. Well, this one, it violates the Huns Rule. Okay, why is that? Because you still have empty space for this electron to occupy over here, okay? Let's look at the third one. We have good, good. How about, this one right here, okay? So this one going the same direction. What is this going to be? This one is violating the Polyexclusion Principle. Well, now, why is it important to understand this 3 rule? Because by looking at this electron in orbital diagram, we can actually determine the properties of different elements. So let's look at one example. Well, you have heard of the term ground state before. When we ask you to write the ground state electron configuration for an element, we're basically asking you to use the periodic table to write an electron configuration in its lowest energy level state. And that is, of course, the electron is occupying at the lowest available energy level. But let's look at this one right here. And this is written based on the Aufbau principle and the Huns Rule, okay? And the way it works is that, of course, based on the Aufbau principle, you have 1s, 2s, and 2p, and so on. And as you fill in the electron, they will fill in the first, or the lowest energy level first, followed by the next one, and followed by the next one, okay? And you're not going to, of course, do this. You have to occupy the empty orbitals first, okay? So let's look at this one right here. So if I'm going to illustrate this to you in terms of an orbital diagram, of course, look at this right here. We have this 1s2, 2s2, 2p6. But what happened when electron exposed to energy and some form of radiation? And this electron become excited, right? Electron are very sensitive to energy. If it has enough energy, it would energize, it would move up to the next orbitals. And now we have the other term, instead of ground state, from the ground, we get excited, we go up. So we have the term called excited state. So how do you know if you look at electron configuration, the electron now is become excited? Well, look at this. We have 1s2, 2s1, and 2p6. What do you notice here? one of the electron in that S sublevel at energy level 2 is now jumping to the 2p sublevel. And this can be moving on to 3s1 as well, and so on. You see the logic behind that? So when electron are being exposed to energy, is absorbing all those energy, and it could be to the point that if it's enough energy, it's going to be so excited, it's going to escape from the atom. So the atom just going to eject that electron. Electron just going to fly off, okay? And we're going to learn that in the next topic when we look at how can we determine if electron and how much energy it takes to kick off an electron at a specific energy level in that specific sublevel. Now, let's go back and look at the properties of elements based on the electron configuration. Well, by looking at the configuration, we know that electrons are very sensitive, right? They can transfer from one atom to another atom. And that's the key. When they do that, it changes the chemical properties of that specific atom. So based on the electron configuration of an element, based on the electron configuration, we can determine if it's going to gain, lose, or share electron in a chemical bond with other atoms. And the reason they do that because they want to have a stable electron configuration. And on your periodic table, the only main group considered as stable is the noble gas. And sometimes you use the term inert. Inert is a common term that we use to replace the word noble. So inert elements are a very stable element. They don't react with other atoms that nearby, okay, or any other elements. That's why other noble gases, see helium, neon, xenon, argon, they exist as a single molecule by itself because they are super stable because they have electron configuration that are stable. So guess what? All the other atoms on the periodic table want to be stable as well. So what they do is, of course, they lose or gain electron. So if we go back and review the periodic table, this right here is your noble gas right here, right? Like, for example, right here, group 1A, 2A, 3A. So instead of going all the way over here to the next noble gas, they will lose their valence electron. For example, in this case, if you notice right here, right, 2s2, 2p1, where is that? That is right here. So what they're going to do is they're going to lose this valence electron and has the same electron configuration as helium. And let's look at this one right here. We have 2p6 and 3s2. Well, notice right here, this right here, 2p6 is what? It is right here at the very end, which is neon. So we pass neon, so we have 3s2. So instead of go all the way down here to become argon, well, would you have electron configuration like argon? That's too far. So what they do, they lose this and it has the electron configuration of neon. And that's the main reason why, as you can see, atoms that are on group 1A, 3A, and 3A, especially metals, they lose their valence electron to have that same electron configuration as the previous noble gas. Now, on the other hand, for group 5A through 7A, which is very near to the next noble gas here, right? 5, 6, 7. All that you do is go through a few more steps, gaining a few more electrons. So those elements or atoms would likely gain electron to have the same electron configuration of the next noble gas. For example, in this case, we have 2s2, 2p4, which is right here, p4, 1, 2, 3, 4, oxygen, right? For oxygen, just 1, 2. So it's going to gain 2 more electrons to have the same electron configuration as neon. And then for the next one, we have argon down here, and then we followed by D, okay, cool, so good, and 4s2, and in this case, probably 4p5, which is right here. In this case, bromine. So bromine, it just only need one more. So that's why bromine is going to gain 1 electron. Isn't that amazing? And lastly, we have group 4A right in the middle. Okay, right in the middle. And we talk about the octet rule. You have learned this a lot of time throughout middle school or even freshman year. Octet rule is basically atoms, they want to gain enough 8 valence electron or have 8 valence electron to be stable, except for the noble gas in previous one, right? So in this case, 4 is right in the middle. So guess what you're going to do if you have 4 valence electron? In this case, instead of gaining or losing, it actually favors both, and that is sharing electron. It is so more efficient to share. Have you ever heard the term sharing is caring? Well, in this case, nature taking it to the next level. It is so well to share with other atoms that you have carbon silicon. It has to be to the point that all living thing on this planet, okay, considered as organic, okay, that's because of the carbon right here. Because every organic matter has what? Carbon. And that's the power of sharing electron. And let's go on to the next one. Now let's move on to the next property that we are going to talk about using electron configuration, and that is magnetism. By looking at electron configuration in orbital diagram, we can determine if an element or substance is paramagnetic or diamagnetic. While paramagnetic, they will contain one or more of unpaired. So for example right here, right, if I have this right here, so this right here, if I have this right there, 1, 2, and go back. See this right here is considered as unpaired. So if a substance has one or more unpaired orbitals and exists and it has a magnetic characteristic, it is paramagnetic. Where diamagnetic, it would not have any unpaired orbitals at all. So that is how you use electron configuration to determine properties of different type of elements on the periodic table. And we'll see you next time on another exciting chemistry lesson.